Okay, so we were in chapter 17, we have finished chapter 17, and now today we are going to start with chapter 19. Chapter 19 is about numerical integration, and in this chapter we will see what we mean by numerical integration, and then we'll see two types of formulas, which are the Newton-Cotes formulas, and we'll take the single application and we'll take the composite application of these formulas. Now, going back to the bungee jumper example, remember we can find the velocity that we have derived from the first chapter. We can find velocity as a function of time according to this equation. Now, suppose you would like to know the vertical distance the jumper has fallen after a certain time. So what we do is, to find that distance, you have to integrate from 0 to time, integrate the velocity. You know that velocity is distance, if he's calling it z here, dz over dt. If you want to find z, you say dz equal to v dt, and then you integrate both sides. You'll get z is equal to integration of v dt. Velocity is given here as a function of time, and now we want to integrate it. Now you can see that integrating this equation is a bit of a difficult task. Yeah, it's not something easy. You can do it, and you can have this analytical solution or closed form solution, but it is a bit of a difficult integration. And of course, you could come across functions that are very complicated, too difficult to integrate, or you could have such that you simply cannot integrate them analytically. In that case, then you have to resort to numerical integration. What do we mean by integration? If you remember, the integration of a function from a to b is defined as the area under the curve, as the area under the curve. So this is the mathematical definition of it. It is the area under the curve for a function. Now we can take this and use the idea to something like this, that if you are plotting it on a graph paper, let's say, and we know that each square, let's say, has certain unit, certain area, let's say small a. No, we already have small a here. No, let's not call it small a. Let me call it I, let's say. So each of the small squares has an area of I. Then what you can do is you can count. We have 1, 2, 3, 4, 5, 6, and you can count how many total, let's say, n squares we have. Then you can find the area is n, the number of squares multiplied by the area of the individual square. So you can do that, and you can find the area. Of course, you will have some inaccuracy in your values, because you are going to miss some part here because you did not include that. You did not include this part, so you are going to have some error here. You are including, and some extra area here, some extra area here, some extra here. So you end up with some errors in your results because of these corners here and there. Either they are not included or included, and then you get some errors. Of course, will depend again on the resolution of the graph. Now, just like we can use the squares, we can use an idea of the strips. So you can divide the whole thing into rectangles, and then you can add the area of the rectangles. So you could take it as, let's say, from A to B, you could take it as one square or one rectangle, and that is going to give you errors. Or you could break them into different smaller rectangles and then add the areas of these rectangles. Of course, again, you are going to get some errors because of the things you either leave or you add extra into your rectangles. So those are ideas that are used when we find areas under the curve numerically. The common numerical integration schemes that we have, they are called the Newton-Cotes formulas, named after Newton, of course, who came up with these methods, and Cotes is one of the students of Newton, and then he has developed them further. They say that you can integrate a function f of x from a to b by approximating this function to a nth order interpolating polynomial. So like we have taken the interpolating polynomials in chapter 17, you could estimate the function using an nth order interpolating polynomial, and then of course we know the integration of polynomial is very simple. So if you, for example, replace the function with a second order interpolating polynomial, then we know that integral of this is going to be so it's a simple integration. Once you have a polynomial, the integration is simple. So you could replace the function with an nth order interpolating polynomial, and then you can find the integral of that polynomial. The integrating function, of course, can be polynomial, or it could be just a straight line, which is a first order polynomial. And then we can take this integral either in one step, like we are doing it here, or we can take them in series of steps. We have two types of methods that are used. We have the Newton-Cotes closed formula, which include both the endpoints, and among them we have the trapezoidal rule, which is a linear fitting to the function. We have quadratic fitting, which is Simpson's 1/3 rule. We have Simpson's 3/8 rule, which is cubic fitting. We have a fourth order fitting, and we have higher order methods. We'll not cover these, we'll only stick to the first three. Then we have the Newton-Cotes open formula, and these formula don't include the endpoints. They only include the interior points, and those are the midpoint rule and the higher order methods. We are not going to cover the open methods in this chapter. We'll just cover the closed forms. That's the open method. It includes the endpoints. In the open methods, you don't include the endpoints. They are not included, and you include only the interior points. So that's the difference between the closed and the open integration methods. The first and the simplest one is the trapezoidal rule, and this is based on a straight line approximation to the fitting. Now you can see that we have a function here, and we approximate the function to be a linear function between the curve. Now what we get here is a trapezoid. We call this shape, we call it a trapezoidal shape, and it has an area given by half multiplied by sum of the parallel sides, which are these two. These are the parallel sides multiplied by the base. That's the base. So that's the area of the trapezoidal. So since the shape becomes a trapezoidal, so you approximate your area to be the area of this trapezoidal, which is given as half sum of the parallel sides. The length here is FA. The length here is f of b multiplied by the base is the distance here, which is b minus a. So we can write it as, if I bring the b minus a first, we can write the area as this, and then we say that our integral is equal to the area. So that's the equation we get for the trapezoidal rule. The method that is used here, if you see it, is based on the Newton interpolating polynomial. So he's replacing it by the Newton interpolation polynomial. If you remember, you had the equation of f1 plus f2 minus f1 over x2 minus x1 x minus x1. If you remember this equation that we had for Newton interpolating polynomial for the first order, so that's the interpolating polynomial that he's using here and finding the answers. So point 1 is a and point 2 is b, and then he's interpolating between them and giving this, and then of course he's integrating this function. He says use the trapezoidal rule to numerically integrate this function from a equal to 0 to b equal to 0.8, and says that note that the exact value can be determined as 1.640533. I'll take this and go to the whiteboard. Okay, so we have the equation given to us, and we want to find the integral using the trapezoidal method. So we say integral is b minus a multiplied by f of a plus f of b divided by 2. So we need to find f of a and f of b. In our case, of course, a is 0 and b is 0.8. So function of 0 is 0.2 plus 25 into 0 minus 200 into 0 plus, so everything else is 0, so it will remain as 0.2. Function of 0.8 is 0.2. I'll bring my calculator. So I have 0.2. I'll add it to the memory. I have 25 divided by 0.8. I have minus 200 x square, so that's x square multiplied by 200 minus, and I add it to the, I have plus 675 x cube, so I have 0.8 to the power 3 multiplied by 675. I have minus 900 x to the power 4, so I have 0.8 power 4 multiplied by 900 is minus, I add that to the memory, and I have 0.8 to the power 5 multiplied by 400, and I add that to the memory, and I get 0.232. Now I can find the integral as b minus a, which is 0.8 minus 0, f of a, which is 0.2, plus f of b, which is 0.232, divided by 2. So I get 0.8 multiplied by 0.2 plus 0.2, this is 0.432 divided by 2. So 0.8 multiplied by 0.432 divided by, so that's the answer I get using the trapezoidal rule. He says that's the exact value that you can find in analytically. If we calculate the error, the true error, it's the true value minus the approximated value over the true value multiplied, of course, by 100%. Plus 1.64053 divided by 1.64053. Oh, 89.5%. So we have an error of 89.5% when we apply the trapezoidal rule to find this value. You can see the actual value is 1.64. We have found 0.17. It's almost 1/10 of the actual value. So this is the application of the trapezoidal rule. We can estimate the error. Now this is the function. It is shown for the same example. You can see that this, the actual function shape is like this, and then once you take a straight line approximation, we get this. What we have calculated is 0.1728 is this area, and then all this big area that comes out as an error. Therefore you find 89.5% error. If we find the error estimate, then the absolute true error comes out to be minus 1/12. Second derivative at a point xi. Remember what we mean by xi. Xi is, we say that between point A and B we'll have at least one point where the slope of the function is exactly the same as the straight line joining the two points. Might be here we have the same slope, could be here also we have the same slope, so we could have 2 points here where we have the same slope. So at that point we call it xi. So it depends on the second derivative at that point, and b minus a to the power 3. Now from this formula we can see two things, that the error depends on the curvature of the actual function as well as the distance between the the 2 points. Now if you want to integrate from 0 to 0.8, you cannot say that I'll not take a big distance, I'll just go from 0 to 0.1. You cannot do that. You have to integrate up to 0.8. And the function is what is given to you. You cannot change the function and say that I'll have something which has a smaller value for the second derivative. Now you can see that if you have a straight line function like ax plus b, then the first derivative is a, second derivative is 0. So in that case, the error is going to be 0. If your function already is a straight line function, then your derivative second derivative becomes 0, and your error will become 0. But if it is some other function which has significant curvature, then of course, depending on whatever value you get of this, you will have error. And of course, it depends on the distance. Now, we cannot change the fact that we have to integrate from 0 to 0.8. But what we can do it is that instead of integrating it all at once, we can break it into parts and then integrate each part and then add up all the areas. So you go from here to here, make a trapezoidal, and you add it. Then from here to here, you make a trapezoidal and you add it. And you see that once you do this, you are going to be adding more of the area. You lose a bit area here, a bit of an area here, but you are also adding some extra area here. So you can somehow try to manage the error and reduce it instead of getting such a big error like this. We call this the composite trapezoidal rule, where you are having more than one application of the trapezoidal rule at one time. Now once you add the areas, then if you go from 0 to 1, from x0 to x1, then your integration formula is b minus a f of a plus f of b divided by 2. So that's the first one. Then the second one is b minus a f of a plus f of b. So that's the second one, and so on. You keep adding them. The third one will be x3 minus x2 f of x2 plus f of x3 divided by 2. Now if you say that all these are equally spaced, and we say that they are of the size h, so that x2 minus x1 is same as x3 minus x2, which is same as x4 minus x3, and they're all, we call them equal to h, so the distance is equal. Then you can replace all these by h. And you can take this 2 out, so you have h over 2 as a common factor, and inside you'll be left with, now if you take h over 2, you'll be left with f of x0 plus f of x1 plus f of x1 plus f of x2 plus f of x2 plus f of x3. So you see that the first one and the last one appear only once. The middle ones, they all appear twice. So you can say that f of x0, which is the first point, and f of xn, which is the last point, then from 1 to n minus 1, the function values, you are going to multiply them all by 2. So that's the composite trapezoidal rule. The error of this composite trapezoidal rule is given by b minus a to the power 3, just like we had it in the single one, and n cube, and the second derivative at epsilon. Now we can see that the greater the value of n, the smaller will be the error. We cannot change this. The function is fixed, it will remain same. We cannot change b and a, those are fixed. The only thing that we can do is we can change the value of n. The bigger the value of n, the smaller the error. You can see that if n is 1, then the error will be whatever error you find, because n cube is 1. If n is 2, then 2 cube is 8, so the error becomes 8 times of it. If n is 3, then the error becomes 27 times of the actual error. So this is how, by applying greater values of n, we can reduce the error. And then of course if you add them all up, it goes to n square, so that if the number of segments is doubled, it says the truncation error will be quartered. So it depends on the square of the value of n. Now he says use the composite trapezoidal rule to find the same thing. We are having the same function and we are using the composite trapezoidal rule. Now we have a as 0, we have b as 0.8. Now the single application, we have seen it when n was equal to 1. Now if n is equal to 2, it means that we are going to have 3 points in that case. N is 1, so you have x0 and you have x1. N is 2 means you have 2 segments, so you will have x0, x1 and x2. In that case, x0 is 0, x2 is 0.8, and x1 is what lies in the middle, so it will be 0.4, which is in the middle of this. F of 0 and f of 0.8, we already found it to be 0.2, and we found this to be 0.232. F of 0.4, we'll find it now. So clear the memory, clear everything. So 0.2, add it to the memory. 0.4 multiplied by 25, 0.4 square multiplied by 200 minus 32, add it to the memory. 0.4 to the power 3 and the memory. 0.4 to the power 4 multiplied by 900 negative, and add this to the memory, and 0.4 to the power 5 multiplied by 400 and add that to the memory, and we get 2.456. Now the composite rule says that the integral is approximately equal to b minus a now becomes h over 2. H is the distance between any 2 points, so 0.4 minus 0, which is 0.4, or h is 0.8 minus 0.4, which is still 0.4. It has to be same. So h is 0.4 over 2. The endpoints, you add the function value once. Whatever is in the middle, you multiply it by 2. Please remember that here we have the function values. Here we have the function values. Some students get confused and they put the x values here. So we have 2.456 multiplied by 2 plus 0.2 plus 0.232 multiplied by 0.4 and divided by, so we get a value of 1.068. The true error is the actual value 1.640533 minus the approximate value over the true value. So this plus 1.640533 divided 1.640533. So we get 34.8% error. So from the 89.5, you were able to bring it down to 34.8% error. Remember the formula that we said n square was for the absolute error, not for the relative error. So don't say that why haven't it we found it to become less by 4 times, because we are not talking about the ET, we are talking about the epsilon. Now what if we make it n equal to 3? So we'll have, if I go back to the graph here now, I make 3 segments, 1, 2, and 3. So I'll have x0, I'll have x1, I'll have x2, and I'll have x3. So I have x0, x1, x2, and x3. So this is 0, this is 0.8. In between, the values have to be so that each one is equal. How can we make sure they are equal? We can use this equation, h is b minus a over n, where n is the number of segments. So 0.8 minus 0 over number of segments is 3. So it is 0.8 over 3. So that comes out to be 0.267. So x1 is going to be x0 plus h. So that's going to be 0 plus 0.267. So it is x2 is going to be x1 plus h. So that's going to be 0.267 plus 0.267. So it means just this number multiplied by 2 comes out to be 0.533. And then the next point should be 0.533 plus 0.266666666 whatever, and it should come out to be exactly 0.8. Of course, without the approximation, it should come out to be exactly that value. So this is how you find the intermediate points using the h. Don't just take it 0, 0.2, 0.4, 0.8. No, it doesn't work that way. You have to have them equally spaced. Some students just take any value, 0, 0.8. So let me take 0.2 increments. So I'll have 0.2, 0.4. But at the end, you didn't have 0.2. You have increased them. Here, the number has increased. So make sure you find the exact value of h using this formula. Now we need the function values. F of 0 is 0.2. F of 0.8 is 0.232. We need f of 0.267 and we need f of 0.533. Now to save time, let me just quickly do it here. 0.2 add it to the memory, 0.267. That is y. equation. By 25, and back to the memory, 0.267 square multiplied by 200, and that to the memory, 0.267 over 3 multiplied by 675, and that to the memory, 0.267 to the power 4 multiplied by 900 minus, and that to the memory, 0.267 to the power 5 multiplied by 400, add that to the memory, and we get 0.89135. Then we have 0.2, 0.533 multiplied by 25, add that to the memory, 0.533 square multiplied by 200, just subtract that from the memory, 0.533 to the power 3 multiplied by 675, add that to the memory, 0.533 to the power 4 multiplied by 900, add that from the memory, 0.53 to the power 5, add that to the memory, and we get 3.48605. Okay, now our integral is h, which is 0.267 divided by 2, 0.2 plus 0.232, the endpoints, and inside everything multiplied by 2, so 0.89135 plus 3.48605. So 0.89135 plus 3.48605, which is multiplied by 2, plus 0.2 plus 0.232 multiplied by h divided by 2, so we get 1.22644, let's say, better than 1.0688. We can find the error as, I'll just put a negative on this number, plus 1.640533 divided by 1.64053. That's 25% error. So we were able to reduce the error to 25% from 34% by increasing the value of n. I'll stop here. Please, if you have any questions.